We're going to go over a exercise that we developed for Webmo. I'm just going to go over the exercise itself, go through the entire thing, explain what the exercise consists of and what the goal of the exercise was, and what we hope to teach through the use of this program. So let's get started. So here we're in the Webmo build molecule workspace, and I've already built a molecule here, but let me just explain what the exercise itself is. So in the problem that the high school student is given, they are asked to build a series of cyclic molecules, including the one that's in the screen currently. So as you can see, this is cyclopropane. It's a three-membered ring, so it's got all of its hydrogens on there, and so they're given a three-membered ring, a four-membered ring, a five-membered ring, and a six-membered ring. And they're asked to build all of these rings in the workspace and use the tools that Webmo has to determine its strain energy of each one. But before they do that, they need to predict, solely based off the geometry, before they go to build anything, which molecules are going to be more stable. So is a six-membered ring going to be more stable than a three-membered ring, or the opposite way around, and why? Why do these instabilities come up? So let's begin with this molecule. So we have cyclopropane in the workspace, and you can see that it's not exactly a perfect tetrahedron about each carbon molecule. It looks like this angle here between the bonds is a little bit strained, and so that could provide a source of strain for us. But let's determine this quantitatively. So we go into the cleanup menu, mechanics, energy. So, and it'll give us right here this total strain energy. And they should write that number down, record it somewhere. So 167. Fine. So let's go ahead and build the next one. So we're just going to delete that whole thing. 1, 2, 3, 4 carbons. Connect them all. Then we're going to hydrate everything. It looks kind of weird, so in our tutorial we're going to explain how to make sure that the geometries come out okay, because it's pretty impossible to draw everything exactly the way it should be. So we're going to go up to clean up geometry. So there we go. So it should be a square. So this is cyclobutane. Let's take a look at the energy for this. So 28. So that's a pretty big difference. So last time this bond-to-bond angle was 60 degrees, now it's 90, and I believe that in normal tetrahedron it's actually 109.5 degrees. So the angle is a bit better, and that's actually compensated a lot for our stability, so the energy has dropped a bunch. So the students should realize that this molecule is a lot more stable than cyclopropane, and they're gonna, after they've built all these molecules and established a pattern of what's more stable than what, they're gonna try and come away with it with some sort of message. So hopefully they'll come away with it thinking that molecules that deviate from their normal geometries will often be unstable and rare in nature. So with that in mind, let's go ahead and build the next one and see what the energy is for that. 1, 2, 3, 4, 5. I think we can just connect these all. Oh, that's awful. Okay, so we're going to clean up, add hydrogens, and geometry. Okay, so this is now a pentagon, the way it should be. Alright, go around and rotate it. It's still planar, although it shouldn't be. Let's see if it'll Yeah, okay, so this is an interesting thing. So with cyclopropane and cyclobutane, both molecules were planar because that was the lowest energy geometry that it could assume. But here with cyclopentane, since it has more members in the ring, it's more flexible. So it'll try to compensate for the strain energy that's going on here, and will bend one atom out of the plane to conform to the 109.5 degrees that a tetrahedron normally does. So let's see what the energy is for this. So again, so we went from, what was it, 167 to 28 to 11. So it's kind of an exponential drop in energy. And I believe if we make this planar, right? So, I see. Let's go back. Okay, so this was planar, and let's try to mechanics energy. All right. Okay, so we increased the strain energy by 5 kilocals. So the molecule is trying to adopt a geometry that will minimize its energy and make it more stable. And hopefully the high school students will try to understand what is going on here in terms of energy. So energy has a really big impact on the structures of molecules. So let's go on to the last one, cyclohexane. We're going to delete all this. 1, 2, 3, 4, 5, 6. Oh, that didn't do anything. Connect all these. And add hydrogens and let's see, idealized. Okay, so let's take a look at this. Alright, so this has done what we would think it would do. It is assuming a chair conformation. Let's take a look at the energy real quick. Energy. So it's only 6.5 compared to 11 in cyclopentane. And you can see that it's doing the same kind of thing as in cyclopentane. So it has this 1, 2, 3, 4, 5 membered. And one of them is out of the plane and it's doing the exact same thing down here. So we can imagine that if this one were bent up here, that this hydrogen would come into contact with that one, and that could cause some electrostatic instability, and that's why it's trying to adopt a conformation like this one. So you can see that around each carbon atom, it's trying to expand this angle that will match this angle. So this angle and this angle will all try to be the same, so that it keeps all of the electrostatic aspects as far apart as possible. So we're looking at a conformation that is most energetically favorable. So this is the last part of the exercise, and so this demonstrates a few things. One is that the more a molecule deviates, the more the molecule is forced to assume a shape that is different than what it's supposed to be, then one that will bring like charges closer together than they can be. It will make it more unstable, and molecules will seek to adopt conformations like this one to avoid those kinds of instability. And so they can view that qualitatively with this strain energy gauge and mark down the trends that are there, and also qualitatively look at the geometry itself and try to infer, like, why does the shape or the conformation tell you something about the relative energy. So hopefully this exercise will demonstrate a lot about molecule stability, and the great thing about it is that you can build things in 3D with no extra parts. It's all in the computer, and it's very easy to visualize. This rotate tool is really great. You can zoom in as well and look at it very up close, and and it's a really great tool. So hopefully this will be as effective as we want it to be. So thank you for listening.